Morning, I'm Spot on Weather, meteorologist Matthew Euler. Welcome to my latest training video. This morning we're going to tackle the topic of temperature and energy. For today's overview of the video, we're going to look at radiation principles, the greenhouse effect, scattering types, as well as the Earth-Sun heat budget. So we'll start off with talking about the emission of solar radiation. Now, the sun, it emits or sends out its energy in the form of radiation. The solar radiation is going to propagate or move through space as these electromagnetic waves or EM waves. The thing with electromagnetic waves is they have both electrical and magnetic properties. These EM waves are going to bombard the Earth, and energy is released as the Earth absorbs it from the sun. Here is an example on the left of electromagnetic waves and kind of like some of the terminology associated with EM waves. The first term we'll talk about is the crest, and this is basically the peak of that EM wave, or the highest point of the EM wave. The lowest point of the EM wave is known as a trough, and wavelength of an EM wave is measured from crest to crest, or high point of one wave to the high point of the next wave, or it can also be measured from trough, the lowest point of one wave, to trough, the lowest point of the next wave. So these are three terms that really are important to understand when we talk about any type of waves. Specifically EM waves, crests, troughs, and wavelength. Again, these electromagnetic waves, they contain both electrical and magnetic properties. That's why they're called electromagnetic. They're in the form of these low points, troughs, as I just mentioned, and the high points, or sometimes we call it crest or ridge. But it's the same terminology here. I'm showing you a diagram of the crest being the highest point or peak of the wave. You can also refer to that crest as the ridge. If you were to take a rope, for example, and kind of just like move it really quickly up and down, you would notice that waves form along that rope. You'll see both high and low points. So take a rope and really like shake it up and down really quick. Specifically, if you had another person holding the other end of the rope, if you and another person had opposite ends of the rope and you shook it really quick with each other, you would see these high points or these ridges and crests, or these low points, the troughs along that rope. That is very similar to how an EM wave operates. The measurement again of EM waves is done via wavelengths. These are very important. This is the horizontal distance between, again, those two successive high points or ridges or crests, or two successive low points, the troughs. Okay, so let's continue on with our discussion here. We know kind of like what electromagnetic waves are, and we know what a wavelength is. One thing we need to understand is these wavelengths are going to vary greatly in size, from gamma rays all the way to radio waves. There's something that's known as the EM spectrum, the electromagnetic spectrum, and on one end are very intense short wavelength type waves. On the opposite end, we have very long wavelength type waves. Visible light wavelengths will generally vary from very small or short, with violet, that color violet being the shortest wavelength, and red the longest wavelength in the EM spectrum. The sun emits most of its energy at wavelengths that are less than 2 micrometers, which is referred to as shortwave radiation. So along that spectrum, the sun is going to emit shorter wavelength radiation. With this solar shortwave radiation, the sun emits radiation at all the wavelengths, but primarily in the visible portion of the EM spectrum. You see this nearly 44% of the sun's energy is in the form of shortwave radiation, and it's emitted in that visible region within the spectrum. Peak intensity is corresponding to the blue and green color, and this shortwave radiation really is going to heat up our planet, and you could definitely feel the difference in that incoming shortwave solar radiation, when you feel the temperatures when you're out in the sun in the summer vice the winter time. It's a big difference of how much more intense incoming shortwave solar radiation is during the summer season as compared to winter. For solar shortwave radiation, most of the incoming radiation hits the Earth at latitudes below 36 degrees or from the middle latitudes to the tropics. And this is why the tropics are generally much warmer than the polar areas, for example. The Earth-Sun relationship, the sun is most intense. It's going to send more intense short-wave solar radiation at the Earth's latitudes at 36 degrees and closer to the equator, basically to the tropics. This corresponding temperature of shortwave radiation on the sun's surface, by the way, is 10,500 degrees Fahrenheit. I mean, can you imagine? That's some crazy intense heat of the shortwave radiation on the sun's surface. 10,500 degrees Fahrenheit on the sun. The radiant energy is going to decrease as the distance increases, and that's really due to some things that we're going to talk about here in a bit. But that radiant energy is going to fan out over longer distance. So for example, you take twice the distance from the source that's emitting the radiation, it's going to result in energy spread out over 4 times the area. Wavelength and temperature now. We know what a wavelength is in relation to EM waves. Let's talk about how the different wavelengths impact temperature. These different size wavelengths can carry out different amounts of energy. Shorter wavelengths are generally going to carry out more energy than longer wavelengths. The size of that wavelength depends on the temperature of the object. Increased temperatures generally are going to mean that we're going to have decreased or shorter wavelengths. When the temperatures are hot, we have shorter wavelengths. When the temperatures of an object are cooler, we have increased or longer wavelengths. Over here on the right-hand side, it looks like a heart, almost like an EKG here. But there's varying degrees of wavelengths here along these lines, okay? That's all I want you to think about. And of course, the high points of these lines in particular are the ridges or the crests, and the low points are the troughs. But in general, different size wavelengths in the atmosphere are going to produce different sort of energy distribution. Here's an example of the size of the wavelength and the temperature. So when we think about size of wavelength, it's inversely proportional to temperature. So the first set of waves here we have, these are shorter wavelengths, okay? And this is solar emission. This is a typical shortwave solar radiation wavelength that you'd see. Notice though, the terrestrial wavelength here on the bottom, look at the size of these waves now. You notice that they're larger wavelengths. And this is going to, basically the shorter the wavelength, the hotter the temperature of the object. The longer the wavelength, the cooler the temperature of the object. And if I just were to draw out the wavelengths, right? Let's do this right here, right now. So we're talking about the sun's shortwave solar radiation right here in this particular example. Just let's compare wavelengths. We do crest to crest or ridge to ridge, right? These are wavelengths. I could go trough to trough as well, and that's a wavelength. But the distance here, okay, is much shorter, let's say, than the distance down here. Okay, you notice that? Compare these wavelength distances. I have a much shorter wavelength up here, and the sun's going to emit that shorter solar radiation wavelength. Whereas the Earth, this is the Earth right here, terrestrial, it's going to emit much longer wavelengths of radiation because the Earth is cooler. All right, now, what can happen to some of the solar radiation as it moves through the atmosphere? Some of this radiation is going to be absorbed. And absorption is generally going to occur when you have this EM energy that's absorbed by a substance. You can imagine, for an example, let's talk about a sponge or even a paper towel. So you basically use a sponge or paper towel to soak up a spilled milk as an example. And what happens is the sponge or the paper towel are going to absorb that milk rather readily. Same thing goes on with the process of absorption in the atmosphere. It's the absorption of this incoming solar radiation. Earth is going to stay warm through absorption of the solar shortwave radiation. And by the way, the Earth itself only absorbs 51% of all incoming radiation. And as the radiation passes through the atmosphere before it hits the Earth, there are many different types of gases in the atmosphere that are going to absorb the rest of this radiation. Some of those gases include the water vapor molecules, the carbon dioxide, the CO2, the ozone, which is O3, which is generally going to occur up in the stratosphere. You're going to get the O3 ozone to really absorb that incoming shortwave solar radiation in the stratosphere, and then you have oxygen as well. All right, so let's look at Earth and the sun emission and the absorption process. On the right here is my diagram. I have the sun. It's sending this shortwave solar radiation through the atmosphere, okay? The Earth is going to emit this shortwave radiation, resulting in warming, okay? So down here at the Earth, at the surface, this shortwave radiation, we have about 51% of it being absorbed here at the surface. But where does the other 49% go? Well, there are molecules, like I mentioned, in the atmosphere that act to scatter or absorb or deflect some of this incoming solar radiation. Additionally, we have 19% of the sun's energy is actually absorbed by the atmosphere, and we have to also think about clouds. When we have clouds in the sky, that is a form of water vapor, water droplets. So you're going to have more moisture with clouds in the sky. It's going to absorb a lot of that incoming solar radiation. And that's why on a cloudy day, it tends to be cooler than on a sunny day, because the sun is basically either absorbing or reflecting a lot of this incoming solar radiation. But just wanted to show you the various differences here. We didn't cover the complete amount of 100% at this point for the incoming absorption rates, but I just wanted to show you some of these examples here in the atmosphere. The clouds, specifically the water vapor, the ozone, the O2 molecules, all this stuff absorbs solar radiation. Now, if the Earth absorbed all incoming solar radiation without re-radiating it to space, we would all basically fry like food in a frying pan. I mean, can you imagine if the Earth absorbed 100% of incoming solar radiation from the sun? My goodness, this would be an uninhabitable planet most likely. However, the Earth takes in or absorbs this shortwave radiation and then re-radiates it as long-wave radiation. So there's a balancing act between the energy in and the energy out between the Earth and the sun. Sun provides the energy in, and again, some of this energy reaches the Earth's surface, some of it gets reflected or scattered. And then the Earth at night, when the sun goes down, starts re-radiating some of this incoming solar radiation it received during the day. And there's a balancing act of energy in, again, equals energy out. The greenhouse effect, some of you may have heard of this, we really maintain our heat balance of incoming shortwave radiation and outgoing Earth long-wave radiation by the atmospheric greenhouse effect. Our planet would be much, much cooler if not for this effect. If we were to say the rate of absorption of solar energy equaled the rate of emission of terrestrial energy, we would basically attain a balance or radiative equilibrium temperature. The temperature really wouldn't change that much in this case if energy in is equal to energy out. Rate of absorption would be the same as the rate of emission by the terrestrial or Earth radiation. And here it is right here. Rate of absorption of solar radiation equals rate of emission of infrared terrestrial radiation. That's one thing I didn't inform you of, but the sun is primarily emitting its radiation in the visible spectrum portion of the EM spectrum, the visible portion, and the Earth is emitting long-wave infrared radiation. So Earth emits, because it's a cooler object, in the infrared portion of the EM spectrum. For the greenhouse effect, again, the Earth's atmosphere allows solar radiation in. However, Earth restrains some of this heating from the day that accumulated. It restrains outgoing long-wave terrestrial radiation. There's many types of gases that are greenhouse gases. Okay, you may have heard of this before. Water vapor is one of the many effective greenhouse gases. So let's say on a cloudy night, you have a lot of moisture in the atmosphere. On a cloudier night, the Earth is trying to re-emit that long wave radiation back out to space. But in many cases, that long wave radiation gets deflected back to the Earth's surface. So let me draw this out for you. So let's say this is my cloud here. This is the Earth's surface. And at night, the Earth is trying to, it accumulated heat during the day from the incoming solar radiation. It's trying to send out this long, oh my goodness, sorry guys, long wave. It's trying to send out this Earth long wave radiation at night. But on cloudy nights, what happens is, as that long wave IR radiation tries to escape back to space, it is basically going to be re-deflected back down to the Earth's surface. So what you get on cloudy nights is warmer temperatures. Now, if you didn't have any type of clouds in the sky, let's do an example of that. The Earth is sending off the heat that it built up during the day back out to space via long wave radiation. There are no clouds up here now, right, to block that outgoing long wave radiation. So temperatures are cooler on clear nights as compared to cloudy nights where the temperatures are warmer and the Earth retains the heat. So here's a cloudy sky. Kind of get ahead of myself here, I think. All right, so under a cloudy sky, cloud droplets and CO2 absorb Earth's outgoing long-wave terrestrial radiation, re-radiate back to surface. That is what I just went over with you on, so I'm not going to belabor this point too much. But generally, cloudy skies keep temps warmer at night as compared to clear nights. And I literally just hit this with you guys with this diagram. I'm jumping ahead, apologize for that. But anyway, clouds play a major role in the Earth and Sun radiative balance. Let's just put it that way. All right, so addition to absorption of incoming solar radiation, we also have reflection. Now, this occurs when a surface turns back a portion of the incoming radiation that strikes it. There are some type of energy, is going to hit a surface and it goes back to where it came from, depending on the angle at which it hit that surface. Now, reflection off clouds and Earth account for 24% of all incoming solar radiation. And then the 6% is actually scattered. So you can see reflection plays a large role too when we talk about incoming solar radiation. As that radiation goes to the atmosphere, there's reflection that occurs, and 6% is going to be scattered. So let's take a look at some of these good properties of reflectors. If we have a white or shiny object, they tend to reflect sunlight the best. An example of this would be a fresh coating or pack of snow on the ground in winter. It has what's known as a high reflectivity or a high albedo. So that's why on snow-covered grounds, the temperatures are usually much colder, specifically in the winter, as compared to grounds that don't have snow covered. If you just have a bare ground in winter, some of that incoming solar radiation is going to be absorbed more readily by the ground. But if you have a snowpack, which is white and is very reflective, it's going to send back a lot of the incoming solar radiation back out to space, and it's going to be very, very cold. By the way, a good reflector is going to be a poor absorber. Makes a lot of sense, right? A good absorber, on the other hand, is going to be a poor reflector. So I mean, this makes plenty of sense here. With an object, you're not going to have a good reflector and a good absorber. You're going to have one or the other in most cases. Now, more reflection is going to equal those cooler surface temps, as I talked about with the winter snowpack. You get higher reflectivity, you're going to have cooler surface temps overall. So here's some examples at the bottom of good reflectors. Fresh new snow is a great reflector. This is really responsible for whether we get really frigid air masses to build up over Canada and over the northern U.S. in winter. If we have lower snow amounts and we have bare ground, again, that air mass is not going to reach its fullest cold potential. Thick clouds are also good reflectors. So on days where you get really thick clouds, I've seen this happen a lot. These towering cumulus clouds and cumulonimbus clouds, thunderstorm clouds, are great reflectors of incoming solar radiation. Temperatures really will not get as warm on those days. I've also seen another really good highly reflective type of cloud is a low, thick stratus cloud. This really prevents incoming solar radiation from reaching the surface. And then you have good absorbers over here on the right. Forests are great absorbers. So if you're ever walking and doing trail or hiking in a forest, you may notice that the temperature in the forest may actually be warmer than, let's say, the parking lot where you started from, wherever you parked your car. to do your hike. When you go into the forest, you're going to have much more absorption of incoming solar radiation. So your temperatures actually be warmer in the forest, believe it or not. For over the ocean, the water over the ocean, when you have a high sun angle over the ocean, and specifically if you have a lower sea state, so let's say the waves are minimal, let's say 1 to 3 feet over the ocean, and you have a high sun angle, that's also going to result in very good absorption of incoming solar radiation. Now, when these seas build up and get higher, let's say 3 to 6, 4 to 8 feet, they're going to reflect a lot of that incoming solar radiation off those rough seas. So the smoother the sea, the better the absorption. Reflection, continuing the discussion on reflection, the ratio of the radiation reflected to the total amount of radiation that's coming in to strike the surface, again, that's known as albedo. Here is new snow's reflectivity, or albedo, it's 75 to 95%. So, I mean, this is so very important in wintertime as far as how the air mass feels above the snowpack. Whether, it's going to feel very cold as compared to over bare ground. Thunderstorm tops, very thick, very tall clouds have an average albedo of 60 to 90%. So on days with thunderstorms, again, you typically have cooler surface temps. Forests have an albedo of only 3 to 10%. Isn't that crazy? And water with a high sun angle, about 10% albedo. Let's now turn our attention to another property. This is known as scattering. All right, so solar radiation strikes very small objects, and they could be, water vapor, or these water molecules, air molecules, fine dust could be in the atmosphere, and pollutants. This scattering effect is going to deflect that incoming solar radiation all directions. We call that omnidirectional, omni being all, that scattering occurs. And by the way, it occurs at all wavelengths. So here's an example on the top of this slide. Let's say we have this incoming solar radiation. Here's your short wavelengths. Remember that? The hotter the object, the shorter the wavelengths of emission. Okay, so we have this small object here. This could be a molecule, this could be dust, this could be a salt particle, any kind of pollutant. As the incoming solar radiation moves in and strikes this object, it's going to send scattering in all the different directions. By the way, scattering is responsible for our blue sky that we see on a sunny day. Also responsible for the setting sun being red or orange when it's low on the horizon, and also responsible for the color of haze, which restricts visibility. Now, there are two types of scattering that we'll talk about today in the training. We'll talk about Rayleigh and we'll talk about Mie scattering. With Rayleigh scattering, this is what's responsible for the blue sky, why we see the sky blue. It's scattering that's molecular in nature. On the visible portion of that electromagnetic or EM spectrum, the colors of violet, blue, and green, those wavelengths are shorter than yellow, orange, and red. And these shorter wavelengths are going to be scattered more than the yellow, orange, and red. Look at this. Violet, the color violet is scattered about 10 times more than red light. So as we look at the sky, the scattered waves of those violets, the blues, the greens, they're going to hit our eye from all directions. Remember I said scattering is going to occur, it's going to reflect or scatter off objects in all directions. This is going to cause a sensation of blue light to our eyes, and this is what makes the sky blue. Here's an example graphically. So the sun is out, it's sending its shortwave solar radiation down through the atmosphere, okay? And it's scattering off of these various objects in the atmosphere. It could be molecules, like I mentioned before, water vapor. It could be, dust or pollutants. And as the incoming shortwave radiation scatters in all directions off these objects, we get what appears to be the blue color. And so you see, we call the sky as blue. So bottom line here, again, as sunlight enters the atmosphere, Rayleigh scattering is responsible for the blue sky. But as the sunlight enters the atmosphere, the shorter visible wavelengths, violet, blue, and green, scattered more by atmospheric gases than the longer wavelengths of yellow, orange, and red. And that's why we see the sky as blue. It's really impressive. Mie scattering is responsible for the hazy look to the sky, hazy sky. Mie scattering occurs in all wavelengths of visible light. With a cloud, the droplets equally scatter the incoming light or radiation, and this is perceived as the color white to our eyes. So you wonder why, in addition to haze, why those clouds, those cumulus clouds we see on a warm summer day, why they appear white to us. It's because of the way the Mie scattering is working. The droplets, again, are equally scattering the incoming light, the incoming solar radiation, and it's going to be perceived as the color white. The Mie scattering is the reason why small or thin clouds are going to look white to our eyes. And then hazy conditions and reduced visibilities are the result of, when you get a lot of dust or salt or smoke. Automobile exhaust in big cities can produce hazy conditions over the city, and other pollutants being scattered. Mie scattering, again, sun angle is going to be very important in the scattering process. If the sun is low in the sky, so we have a very low sun angle towards sunrise and sunset, when the sun's first coming up or going down, this incoming solar radiation is going to pass through more of our atmosphere, which is going to increase scattering, resulting in a red or orange sunrise or sunset. Now let's take a look at this. Okay, so let's talk about this for a minute. All right, so when we digest what is said here, during the middle of the day, okay, forgive me for these weird little spokes. I'm trying not to make them, but let's say this is our sun, okay? During the middle of the day, the incoming solar radiation pretty much is going to go straight down, okay? This distance is going to be much shorter when the sun is highest in the sky, say around midday. But let's now go to sunrise or sunset. Let's go to sunrise. Here's the sun again, okay? It's low on the horizon. So the incoming solar radiation is going to be scattered. It's going to have to pass through a much greater distance of the atmosphere, and there's going to be all these little molecules that are going to scatter this light in multiple directions when the sun is low on the horizon. So you're going to get a lot more colorful sunrises and sunsets when you have a lower sun angle because of this shortwave radiation having to pass through a much larger portion of the atmosphere. And that's going to result in greater scattering on the red and orange color spectrum of visible light. So hopefully that makes sense to you. And then finally, we're going to conclude today's training with a look at the Earth-Sun heat budget. Again, energy in equals energy out. That is going to keep our overall Earth temperature constant. Emitted energy from the sun is going to hit the Earth in the form of this shortwave solar radiation, which we've already extensively covered. The Earth is going to absorb this energy and then emit its own radiation in the form of that long wave terrestrial or Earth radiation at night. And as that long wave Earth radiation tries to escape back out to space, we have atmospheric gases which hold it in, and this is known as the greenhouse effect, which keeps our planet very, pretty habitable. One other thing I want to mention, we've got a lot of oceans. If we look at the oceans in the northern hemisphere alone, 60% of the northern hemisphere is covered by ocean water, 40% by land masses. So oceans play even a larger role. Actually, I've mixed that up. Northern hemisphere, 60% is covered by land masses, I believe, and 40% by oceans. It's flipped. I was doing the southern hemisphere first. I apologize for that. But oceans play a big part in the process of the Earth-Sun heat budget. They provide moisture in the cloud formation process. When these clouds form over the ocean, condensation occurs. It releases latent heat to the surrounding air, to the atmosphere. Also, oceans transfer heat from the equator to the poles. And then you have reflection, which occurs where 30% of the incoming solar radiation hits the Earth and is reflected back to space. So we take into account, the sun emitting its shortwave radiation, some of that shortwave radiation being absorbed, some of that shortwave radiation being reflected, and some of that shortwave radiation being scattered in all directions. All of these play a big part in keeping our annual temperature the same year after year, excluding the role of it, as long as we don't include the role of increasing levels of CO2 in the atmosphere. So excluding those increasing CO2 levels, these are the natural built-in mechanisms the atmosphere uses to keep the temperature in check for the Earth. So again, I greatly appreciate your attention to this training video. That wraps it up for me. We covered a lot of material in today's session. We covered the Earth-Sun relationship, the heat budget overall. We talked about radiation principles. We talked about the greenhouse effect, scattering types, the Earth-Sun heat budget. How the sun is a hotter object, emits shorter wavelength radiation. We talked about what an EM wave is, the different parts of the EM wave. We talked about Earth's long wave radiation or infrared radiation. We talked about an accumulation of incoming solar radiation south of 36 degrees latitude, basically between 36 degrees latitude and the tropics, and that's why the tropics are warmer. We examined different wavelength sizes and related them to the temperature, where there's an inverse relationship of the size of the wavelength and the temperature. And then we looked at various things that occur as shortwave radiation interacts with molecules suspended in the atmosphere. We talked about absorption of solar energy. We used an example of a sponge or a paper towel, basically absorbing the liquid that you spilled. We talked about the greenhouse effect again, and how it keeps the Earth habitable and sends back some of the long wave radiation back to Earth. We talked about the difference between temperatures on a cloudy night versus a clear night. And then we talked about reflection, some good reflectors, good absorbers, and then we talked about scattering and why scattering is important. Well, scattering is important because it helps us, it really explains why we see the sky as blue. It also helps us understand why clouds are white, they appear white to us, or we have hazy skies. So I really hope you got a great amount of information out of this training today. Yeah, the oceans are huge, and the way they've been warming, my goodness, the oceans have just been warming so greatly here, and it's no wonder why some of the Earth-Sun heat budget would be thrown off and out of balance if these oceans continue to heat. You see the role that they play in this heat transfer from the equator to the poles. But anyway, that's all I got for now, everybody. Until next time, take care and God bless everyone.